physics and so forth talks about the way that the world works when it's behaving reproducible. And we think that the laws of physics are amazingly consistent. And therefore that, basically most things that happen in the world are in fact in accordance with the laws of physics as we understand them. So the question then arises, can anything happen that is not consistent with the laws of physics or the laws of what we discover about the world generally through science? And the answer is that logically, you can't rule out the possibility that there are things that happen that are not in accordance with what we discover from doing reproducible experiments or observations. So logically, miracles are not ruled out by modern science.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 133, and it is the last of the 3 introductions I am recording for the week after just having gotten my wisdom teeth removed. So this episode, this banger of an episode, if I don't say so myself, is with Ian Hutchinson, who is professor of nuclear science and engineering in the Department of Nuclear Science and Engineering, who would have guessed, and the Plasma Science and Fusion Center at MIT. And while listeners of the show will know that I'm a total physics fanboy, I am unfortunately quite lacking in formal physics education. So this podcast has been a really awesome way for me to get to talk to some of the brightest minds in physics, and there's more to come, about their various areas of expertise. And this for me was a particularly exciting installment because, well, Ian's great. That's one good reason. But another reason is that plasma and nuclear physics are somewhat far from the more mainstream and off-trod physics topics of quantum theory and space and time. So Ian and I talk all about plasma, which is the 4th state of matter. And we do this in the first third of our conversation. And then in the second third, we turn to nuclear physics, though nuclear physics and plasma physics overlap. And in particular, we talk about nuclear fission and fusion. And then in the final third of the episode, we take a turn and we talk about Ian's religious beliefs. So Ian is Christian, and he believes that science and religion are both compatible and complementary. And we talk about how he understands miracles, how he reads religious texts like the Book of Genesis, how his faith informs his work as a physicist, and what he sees as the dangers of scientism. So for full disclosure, I would self-classify as a quite resolute, though by no means militant atheist. But as with any topic covered on the show, I don't see my job here as sharing my own views, though maybe that there will come a point for that if I continue to get nagged about doing solo episodes. But so it's not so much my job to share my views as it is to understand those of others. So I'm incredibly, incredibly thankful to Ian for explaining and sharing his beliefs with me. So explaining his beliefs to me, sharing them with me. And of course, we don't get to everything. And there's a link in the description to Ian's latest book, which is Can a Scientist Believe in Miracles? The answer is yes. And lastly, a note about comments. I do not really moderate the comments on YouTube at all. I've only had to remove a few when there were racial slurs bandied about at some of my guests. And while I'm all for freedom of speech and evidently freedom of cat motion to some limited extent, this is still, in a sense, my house. I'm thinking of my YouTube channel here. And I'm inviting guests to come on, great guests, I might add, and I don't want them to come onto the show and be personally attacked. I have been personally attacked enough that I'm developing a nice, thick skin when I look at comments, but I can't expect that for my guests who don't put out 3 podcast episodes a week. So with that being said, since this episode deals with religion in particular, or religion in general, I guess, and Christianity in particular, while I certainly encourage anyone who disagrees or agrees with Ian and wants to express their thoughts to do leave a comment, but please do so courteously. That's all that I really have to say. So reviews on Apple and Spotify generally, comments and likes on YouTube, subscribes on YouTube, follows, I think, on Spotify and Apple are endlessly appreciated. I love seeing those numbers go up. They make me very happy. And they make it easier for me to continue delivering great guests or the thoughts of great guests to you. So without any further ado, I hope you enjoyed this conversation as much as I enjoyed having it with Ian. And I hope you'll forgive this characterization right off the bat, but I think of the sexier branches of physics as maybe quantum mechanics, cosmology, maybe string theory. I think these are the areas that really capture the popular imagination, at least. And very few outsiders are aware of plasma physics. And to the extent maybe that nuclear physics has a place in the zeitgeist, it concerns atom bombs and recently Oppenheimer. So how was it that plasma and nuclear physics first caught your attention? So what were the research questions that led you to spend your career in the area?
Well, let me change the epithet a little bit by saying that I consider myself to be an applied physicist. And the fields that you cited as being the ones that you regard as being sexy are the currently fundamental areas of physics that, seem to be leading us to brand new knowledge of the laws of nature or the nature of the universe and those kinds of things. So I think that what I'm doing, what I have done in my career, has not been mostly that type of physics. Nuclear physics was once, the cutting edge of discovering the laws of physics, but it hasn't been since, probably the 1960s or 70s. And so what I am doing is pursuing the applications of both nuclear physics, which is nuclear is the name of my department at MIT. I'm a member of the Department of Nuclear Science and Engineering, and that department is interested in the applications of nuclear interactions and nuclear reactions to important things in our society. And I'm also a plasma physicist, which is plasmas are basically one of the key applications of Maxwell's equations, which are the equations of electromagnetism. And so, in that area, I'm studying the ways in which gases of ionized particles, that's what a plasma is, it's a gas of ionized particles, how that interacts with electric and magnetic fields and how it then behaves in very interesting and peculiar ways. And in fact, that has very wide applications. Plasma physics has very wide applications. For one thing, almost all of the visible universe is made up of plasma. The Earth, for example, is a relatively unusual place in having most of its matter not being ionized, unlike stars or galaxies or all sorts of other astrophysical phenomena. And also being very important for applications by us humans to technological development, including, in my case, the possibility of bringing nuclear fusion, the energy source of the sun and stars, down to the terrestrial scale and making it available to humans.
Well, okay. One, thank you at the outset for distinguishing between, one, your work as an applied physicist and then the work on the fundamental aspects of the universe that the other theoretical physicists are working on, because that's important. I don't think I've spoken to an applied physicist on the show so far. It's mainly been theoretical physicists, astrophysicists. So that's very good. I was going to go into, to start out with, just what a plasma is, but you touched on that a bit. And so I'm wondering if we ought to continue for a minute with this distinction between the applied physics and the more theoretical fundamental physics on the other hand. Do you happen to know the name Sean Carroll?
I do.
Okay. So Sean Carroll's a communicator. He works in cosmology and quantum mechanics, and then he's also a philosopher. But he recently did a 4-hour episode of his show about whether or not there's a crisis in physics based on, different conceptions of the notion of crisis and in different areas of physics. But one field he mentioned as not being in any state of crisis whatsoever is plasma physics, though he didn't elaborate on this at all. So first, just as an aside, I'm curious about whether you think there is, in fact, a crisis in physics or crises in physics in any interesting sense. And then second, why there isn't one in plasma physics, if you agree with that.
Well, yeah, that's an interesting follow-up to what I was saying. I do think that there is some kind of slowing down of the fundamental physics that has been developed over the past 200 years to the point now where we have most of what we think to be the fundamental equations that govern, everything that we have in this universe, and that the prospect of us discovering new laws of physics is much less plausible and is happening at a much slower rate than ever before. And some people think that's a crisis of fundamental physics in the sense that, well, what do we do next? We can't build, super colliders that reach the incredibly high energies that are necessary to go to the next step in probing, the basic laws of matter and energy. And so experiment in terms of discovering new laws is at an impasse. Actually, I don't think the impasse is particularly severe, even in fundamental physics. I think actually cosmology is one of the areas where we are still able to discover new results that are experimental in a sense and bear on these fundamental questions. But even if there were a crisis at this fundamental level, or at least the sense that there's slowing down, the things in our world that are complex are equally important as the things that are simple. So it may not seem to most people that the laws of physics are simple, but to physicists, we think there is a great intrinsic or fundamental simplicity to the laws of physics, and yet from those simple laws spring all kinds of complex results, including life and the universe and everything. Okay, and plasma physics is one of the things that springs from those fundamental equations. And plasma physics itself is a very complicated field, and there are new results being discovered all the time, as well as that we're discovering how to apply plasma physics to important human problems and understand the plasmas that are around the Earth and so forth. So we're still very much in a discovery phase of those complexities.
Am I right that much, though, of the complexities of the plasma that you're dealing with now, and we'll get to this more later when we talk about your work in nuclear physics, they're more engineering problems? Is that accurate at all, or are they really purely theoretical problems about how plasma functions?
No, I wouldn't agree they're all engineering problems. I mean, there are lots of engineering problems if you set out to do something specific with plasmas, and the application that has drawn most attention by plasma physicists has been whether we can bring fusion energy to the human scale, and there are many engineering problems that exist within that possibility. But actually, even in that area, most of what's been done in the last 50 years of research on that problem has been basic plasma physics. It's been basic physics. It's been understanding how the laws of physics as we know them work out in practice. And the theories that we do and the experiments that we do, which is also a very important part of physics. Let's not distinguish between theory as being physics and the rest being engineering. That's not true. Physics is both theory and experiment, and these days also simulation. And it's the application of those to practical problems, which is engineering. That's the way I think about things. So I would say that physics is a very fundamental part of what we do in plasmas. There is a division of the American Physical Society, which is the U.S. Society for all physicists, and the membership of that division is as large as most other divisions, except possibly solid state, which is very, very large because of the applications to semiconductor devices of various sorts. And so, certainly plasma physics isn't less a physics field than nuclear physics or high energy physics is, I would argue. And I think that the American Physical Society would agree with me fundamentally. So on the other hand, because of the fact that it is applied physics by and large, there are plenty of people in the field, myself included, who have appointments in the engineering school. So I'm a professor of nuclear science and engineering. My department is in the engineering school at MIT. It's not in the physics department. But that's not unlike lots of other areas of applied physics where applied physicists find themselves in engineering departments rather than in physics departments. Physics is terribly important to society, by the way.
Is.
And I'm not at all ashamed of being in the engineering school.
Right. Well, okay, before we move on, just if I can put my own maybe summary / spin on things and you can respond to just tell me if I'm totally off. But at the very fundamental level, though the classical relativistic picture is very successful in one domain and quantum theory is very successful in another, fundamental physics has slowed down, at least in part. And here's where the crisis might emerge. Because general relativity and quantum theory have thus far remained incommensurable, but plasma and nuclear physics are sufficiently distant from this issue and emerge maybe from the successes of the standard model. And for this reason, it's not subject to the slowing down in fundamental physics.
Well, I think I went along with what you were saying right until your last sentence, okay? Which is that I think it's true that plasmas and nuclear physics are developments of relatively well understood, fundamental, standard model of physics, and that as a result, that their challenges are not subject to the slowing down that has happened because of the difficulty of probing beyond the standard model.
Okay. Yeah. Okay. So we're on the same page. Okay, great. And then, returning back to the main thread of plasma physics for the moment. So if we were talking about gases or liquids or solids, starting at the very technical basics would still be the right place to get started. But despite its being the most plentiful state of matter in the universe, even if that's not the case on Earth, since most people probably associate plasma, either maybe with blood or sci-fi weaponry or something like this, we should probably begin with this. What is plasma? But more particularly, since you've answered this already in general, what are some plasmas maybe that we find on Earth?
Okay. Well, solid, liquid, and gas, are phases of matter. And we sometimes say that there are 3 phases of matter, but those of us who are plasma physicists say, no, that's not correct. There are 4 phases of matter. And as you raise the temperature, you go from solid to liquid to gas. And then if you raise the temperature high enough, then ionization of the atoms that are moving free and molecules that are moving freely in the gas takes place, and you reach the plasma state. That is reached when you get to a temperature of a few thousand degrees Celsius or degrees absolute. Okay, and so beyond that, most virtually all of matter tends to become ionized. When it is ionized, that means the electrons and the nuclei, or at least the ions, the partly neutralized nuclei, are charged particles. And charged particles are influenced, obviously, by electric and magnetic fields. They're pushed around by the fields, the electric and magnetic fields, and those fields become an essential part of the way that form of matter behaves. And as a result, it behaves quite differently in some respects from a solid or a liquid or a gas. It is a fluid, in the sense that it's not stationary in some kind of crystal lattice or material form, but nevertheless it behaves rather differently, and that's because the particles, when they move around, are influenced by the fields, but also they influence the fields. So magnetic fields can be generated by currents, as is rather familiar in lots of situations. So, for example, if we want to make a magnetic field, we can wind some wire into a coil, put current through it, and that'll generate a magnetic field. Similarly, the density or the number of particles per unit volume determines the electric field. So if we put a lot of negative charges in a place, a body that is negatively charged, has an electric field surrounding it, which will attract positive charges towards it. And so there's this interesting fundamental loop of consistency, which is that the plasma is affected by the electric and magnetic fields, but the electric and magnetic fields are affected by the plasma. And in the end, this system has to become self-consistent. And it's the fascination, or it's the exploration of that self-consistency, which is a big part of what we do in plasma physics. So maybe that's enough. You asked about applications. Perhaps your listeners are aware of the fact that they can hear me now basically because of things that are made using plasmas. Virtually all of the solid state devices, chips, and so forth that go into phones and computers and so forth are processed using plasmas interacting with semiconducting materials. And so perhaps the most widespread current terrestrial application of plasmas is to the manufacture of semiconductors, which is what makes our modern technological society possible. There are many other applications, but I would say the other extremely widespread importance of plasmas is in space. Space isn't just a vacuum. It has very, very low density once we get outside of the atmosphere. But actually, the particles in space are mostly ionized. In other words, what is out there in space beyond the Earth's atmosphere is plasma. And in fact, the plasma surrounding the Earth is responsible for all kinds of natural phenomena. So people might be familiar with the aurora borealis, for example, which is the northern lights. Those northern lights are caused by the precipitation of plasma electrons from the surrounding magnetic fields of the Earth into the atmosphere. And so they're a sign of the influence of plasma on our lives. Now, that might seem a pretty distant influence, if you don't live in Alaska or somewhere. But actually, for modern communications, for satellites and things like this, the influence of the plasma around the Earth can be very important. The plasma around the Earth, actually, by the way, is the reason why we can, with wireless, transmit short waves all the way around the Earth, because actually radio waves propagate in straight lines. And so if you had, on the surface of the Earth somewhere, a transmitter, and there were no plasma around the Earth, the signal from that transmitter would just go out in one, half plane, and there would be no way for someone in North America to have radio contact with someone in Australia. But in fact, starting in the early 20th century, people were able to talk to one another around the world because there's a plasma around the Earth that reflects the radio waves back, and they bounce around inside that plasma and can therefore make it from North America to Australia or anywhere else on the globe. So there are a few examples of how important plasmas are to our lives and to our understanding of the world.
Okay, well, you described plasma as a fluid because it's not stationary, but is it fair to say that plasma is closest in similarity to gases? And hopefully you don't think this is silly, but the reason that I ask this, though, is I want listeners to be able to understand on a more visceral level that they might associate with touch or sight, just what plasma is like. And maybe it's impossible to answer this because so much varies on density and temperature. And I mean, you can't touch the sun, for instance, but maybe you do have an answer to this.
Well, actually, although this is a little old-fashioned, fluorescent lights are a very familiar example of a plasma that we used to have in almost all of our rooms in shops and in our homes even. Of course, we're gradually replacing those with semiconductor lighting systems now because they're a bit more efficient. But basically, that's a very cold plasma by my standards. It's the temperature inside that fluorescent tube, let's for example, is essentially it's a gas. It's a rather low density gas. It's a density that is typically much lower, actually, than the air in our rooms. So it's a very tenuous gas, but it is a gas. And what's happening in a fluorescent tube is that the gas in there is being ionized. It's carrying, as a result, being able to carry an electric current, and that electric current heats the gas and causes the neutral particles that are left behind. Not all of the particles are ionized to emit light. So yes, a plasma is a gaseous medium, no question about it. We have a distribution of particles that's moving in random ways with a random set of velocities and directions. But the key difference between that and a neutral gas is this influence and mutual influence with electric and magnetic fields.
Well, this, since you mentioned the low density of fluorescent light plasma, the plasma that's in there, this I just found very interesting that I learned recently. So I have on my desktop is a famous image of the Pillars of Creation, which you'll be familiar with. And so this nebula, is it plasma? I know it's gas. I'm not sure if it's. I know some nebulae are plasma, but
broadly speaking, yes, it is a plasma in the sense that it is a gas that is largely influenced and controlled by electric and magnetic fields. Actually, in astrophysical plasmas, gravity is also extremely important. because of the very large scale of those plasmas. On Earth, gravity is not important for most plasmas because they're smaller, and the gravitational force is therefore much smaller than the electric and magnetic forces. So the answer is yes, it's a plasma. Those of us who are plasma physicists are sometimes a little peeved with our astrophysical colleagues for always calling gaseous media in space gases. For a long time, they've had a headache using the word plasma, and I understand that because it's not so familiar a word as gas for the person in the street. But the fact of the matter is, they are exactly what we call plasmas. In the case of nebulae, though, there are usually other constituents in the plasma. There is dust, and that's usually very, very important in a nebula, in a way that it isn't so important, for example, in a star or let's say in most of the space weather that's going on around the Earth. So it's not a pure plasma. It's got other stuff in it.
Mm-hmm. Well, I actually wanted to get to that dust in a moment, but what I was going to say is, and the reason that this came to my mind based on your mention of the low density plasma in a fluorescent light, is that when you look at these images of the pillars of creation, like I have here, for lack of a better word, these clouds, they look almost tangible. They're so concrete. But what I learned the other day is they are far, far more rarefied even than the air around us by many, many orders of magnitude. They are so not dense. And I just found that fascinating.
To give a specific comparison, if you were to think about a cubic centimeter, so a little box about that big, okay, the plasmas in space around the Earth, the so-called space plasmas, typically have densities of particles that are a few particles per cc, per cubic centimeter. Okay, so that little box would have a few particles in it. The densities in astrophysical and galactic space can be even much lower than that. Okay. That's to compare with how many particles are there in a normal gas in that space. Well, it's probably 10 to the 20th or it's many, many orders of magnitude larger. So there's an enormous difference in density, and the plasmas that I deal with, even on Earth, tend to be much more tenuous than the density of the air at atmospheric pressure around us. There are some plasmas that people are interested in and study that are in atmospheric plasmas. There are some naturally occurring ones, such as the aurora, such as lightning strikes, and so forth like that. And there are also some technological applications of atmospheric pressure plasmas, but usually the density of the charged particles in those is much less than the density of the uncharged particles. So we are often dealing with impure plasmas.
Mm-hmm. Okay, well, speaking of impure plasmas and the dust that you referenced a few minutes ago, I saw that some of your work on plasma physics centers around how flowing plasma interacts with other nearby bodies. And this seems like an area, as we just touched on, in which your work dovetails quite specifically with astrophysics and also, which I find very, very neat, space exploration. So what are some of the absorbing bodies that hot plasma, or maybe it's not always hot, but plasma might interact with that you're concerned with?
Absolutely. So just to talk in terms of an explicit example, people probably have heard of the solar wind. This is a plasma that blows away from the sun at high speed, and it encounters planets. The Earth, an important planet for us, has a magnetic field, and that magnetic field actually strongly influences and, in fact, in many cases stops and causes to flow past without interacting with the atmosphere, the Earth. And so the Earth's magnetic field is very important, actually, protection for planet Earth from the effects of the solar wind, which would otherwise be somewhat problematic. It's one of the unique features about the Earth compared with some other planets. So that's one way in which flowing plasmas interact with bodies. The particular example that I've paid some attention to in the last 10 years has been the interaction of flowing plasmas with the moon. The moon is interesting in that it doesn't have an intrinsic magnetic field, unlike the Earth, which does have a very strong intrinsic magnetic field. And when a plasma interacts with a body that doesn't have an intrinsic magnetic field, the plasma particles more or less come straight down and crash onto the surface of the moon. And what then happens is the plasmas generates electric fields that cause some shielding, and the plasma flows past the moon, leaving a wake along, in the case of the moon, a wake that's perhaps 10 moon radii long. So think of the moon as being a sphere. There's a wake that goes, this far behind it as the plasma solar wind blows past it. And very important things happen in that wake. If you think about wakes on Earth in regular fluids, for example, the wing of an airplane, gas flows past the wing and then it develops all kinds of eddies and important turbulence behind it. Well, the same kind of thing happens in a plasma flowing past the moon. Various interesting things happen in the wake. It's a very different sort of wake than a neutral gas wake. But my research in the last 10 years or so has pursued the interesting question of what happens in that wake. And actually, I showed theoretically that wake ought to have instabilities in it, which generate some phenomena which are called electron holes, which I won't try to explain, but basically they're little solitary waves that are generated from instabilities in the plasma and that move around. And I predicted that the moon's wake would be full of these electron holes. Well, no one knew whether it was. So actually, nevertheless, there had been since about 2011 a NASA mission which had placed in orbit around the moon a couple of satellites that were busily measuring the electric and magnetic fields in the vicinity out to about 10 moon radii. And so those satellites had been gathering data which could answer the question whether my theory was actually borne out in practice, in experiment. It was, in a certain sense, it was an experiment, but it was an observational experiment. And a collaborator of mine, David Malaspina, he and I got together and we said, let's actually analyze this data. And mostly it was his doing to analyze the data. But to make a long story short, he found these holes. So he found that the wake around the wake behind the moon was full of these little electron holes, which are signs of the instability that's taking place in that. So now I say somewhat jokingly, well, when I look up at the moon, what I think of is that on the dark side of the moon, streaming away in the moon's plasma wake, it is full of electron holes that David Malaspina and I discovered. And I find that to be an interesting phenomenon. And I will sometimes joke with my wife that I think it's, quite something that, lovers should look at and think about.
Well, this harkens back to the beginning of our conversation, but in the interest of better understanding the taxonomy within the field, something I don't understand is why this research on, well, just take the electron holes, for example, why this qualifies as applied physics. Maybe this is an instance in which you're not doing applied physics, because I would think maybe if you were researching how when you brought up probes, I thought you were going to say, and we have to understand how the electron holes impact the probes, but that would sound like applied physics to me, whereas this sounds just like pure astrophysics.
Well, arguably, what I've just described is astrophysics, or
Okay.
pure in some sense. I would say it's actually discovery. It's not fundamental physics, but it is physics, a discovery in physics. And it's not obvious that it has an application. Okay, not least not very directly to some kind of new technology. But actually, my interest and my theoretical work that led to this discovery did, in fact, spring from measurements that I had been making in the edges of magnetically confined plasmas that we were studying in order to see if we could make fusion work. And so this was an interesting situation in which very obviously applied physics, fusion research, was interacting with more kind of basic physics, discovery physics, if you like, and there's an important give and take between these two things. So, again, just coming back to this issue of taxonomy, I think it's important to recognize in science that one isn't necessarily always discovering the laws of physics in the sense of the fundamental equations. One is often discovering the consequences of those equations of physics. And that's true in other scientific fields in spades. I mean, if you think about what biology is, when you're discovering things in biology, we take the view that biology is, governed by the laws of physics. But you wouldn't try to do discovery in most situations in biology by writing down Maxwell's equations or the standard model of physics, because you're not operating at that level. You're operating at a different level. And in fact, science as a whole has many different levels at which it operates. And so, if you think of, quarks and gluons as being the fundamental level, and then there are many levels over and above that. And I'm somewhere in the middle in plasma physics, in my professional work. But, in my daily life, I'm somewhere up here. Okay,
Mm-hmm. Well, okay. Before we turn to the nuclear physics, though, I have two questions that go in slightly separate directions. So the first is toward the applied physicist side. You mentioned that the solar wind, for instance, is one plasma that it's quite verified, but we're familiar with, that's astrophysical in nature. And I'm wondering if you work on this or related issues in an applied sense, in that you're curious about, say, how a sail on a probe might interact with the solar wind. The reason this comes to my mind is that you mentioned plasma flowing around the wings of an airplane, well, gas flowing around the wings of an airplane. And then on the flip side, I'm wondering if you do any quite maybe canonical astrophysical work involving plasmas, say modeling the internal activity of a star, how plasma works there.
Well, first of all, yes, people do dream of using sails in space and using the solar wind to, drive spacecraft and so forth. It's not currently in widespread use, and it's mostly science fiction at the moment. But it's in principle could work. Okay, it couldn't do a lot of the things that science fiction writers suppose that it could, but it could do something. So. There can be applications. There are applications of plasmas in space. Also, plasma physics is responsible for many of the things that astronomers see. So, for example, to understand the universe, we mostly, of course, use telescopes to see what's out there. And there are many phenomena out there which are basically governed by plasma physics plus gravity, okay? And these can include, jets and pulsars and blazars and things like that. And so plasma physics has, in a certain sense, practical importance in explaining the things we see in our world around us. And I would say, understanding how a galactic jet works is the same kind of thing as understanding what a lightning strike is. Okay, I mean, it may seem a lot further away, but from the point of view of what are we doing here, we're understanding the world around us. Okay, so I would say that plasma physics is a vital part of that understanding.
Okay, no, great. Well, I have thoroughly loved this, and I'm sure I'm going to love talking about the nuclear physics as well. And here again, there are two questions that occur to me. The first, which is less important than the second, is just how plasma physics and nuclear physics are related. And second, of real crucial significance to our conversation, is how you feel about the movie Oppenheimer, which I mentioned earlier.
Well, I haven't seen it yet, so I can't tell you the answer to that. But I'd be happy to tackle a few of the issues to do with the application of nuclear physics. The main way in which, in my career, plasma physics and nuclear physics has been related is that in nuclear physics, there are two main processes of nuclear reactions. One of them is called the fission reaction, and that is if you take a heavy element like uranium and you break it up by some means, which we can talk about later, then when you do that, it releases energy. And that is the energy source of our current nuclear reactors and of the fission bomb, which was the first form of nuclear bomb, since you raised the question about Oppenheimer. So that's the fission reaction. And that's an important and incredibly powerful way of releasing energy. And nuclear energy in general, just to set the scene, nuclear energy sources are approximately 1 million times more intense per unit mass than chemical forces. So when you make one fission reaction, you get out about 1 million times as much energy as you get from one, let's say, chemical reaction, let's say taking hydrogen and oxygen and making them into water. The second nuclear type of reaction is called a fusion reaction. And that is when you do the opposite. Instead of taking a heavy element like uranium, which has 200 and some number of nucleons in it, you take a light element like hydrogen, which has 1 proton, or its isotopes, which add a neutron or 2 to that proton, or other light elements like lithium and so forth. If you take, let's say, a couple of hydrogen isotopes and react them together, they can, instead of breaking up heavier elements, form a heavier element. In the case of hydrogen, they would form helium. And one can also address heavier reactions. But broadly speaking, a fission reaction is taking particles, gluing them together and getting heavy elements, unlike fission, which is taking heavy elements and breaking them up and getting lighter elements. But fusion reactions also release energy. At least they do when you're down dealing with relatively small elements. And that energy source is the primary energy source of the sun and stars. In other words, the sun shines because of the fusion reactions that are taking place inside of it. So when a star is initially formed, it it comes from neutral gas. The gas compresses, it heats up, it gets ionized, it becomes a plasma. But sooner or later, it gets so hot that it starts to have fusion reactions, and those are then the source of energy in the star. Now, fusion reactions are reactions between charged particles. So a hydrogen nucleus, which is a proton or a proton plus a neutron, or proton plus two neutrons, is positively charged. And if you react it with another hydrogen nucleus, they repel each other. And as a consequence of that electric repulsion of two similar charges, it's quite hard to make fusion reactions take place. You have to smash those nuclei together with rather high energies in the vicinity of hundreds of keV, or maybe tens under some circumstances of keV. Electron volts. We'll come back to. I'll explain this, but basically, energies, the sorts of energies that occur only at millions of degrees Kelvin temperatures, and so that's why in nature fusion reactions take place in the incredibly hot centers of stars and other astrophysical bodies. But if we were able to create hot plasmas on Earth, hot enough so that those fusion reactions can take place, then fusion energy on Earth becomes, at least one hopes, as feasible as fission energy. And that's one of the driving forces that has encouraged scientists for 60 years or more to study plasma physics, understand it better, to understand whether, in fact, it's going to be practical to do that, to generate a well-confined plasma in which the energy doesn't simply leak away straight away, in which the temperature is hot enough for fusion reactions to take place. Now, in a star, the plasmas are held in by gravity. And that's the confinement force. Gravity is the confinement force that holds the star together and enables it to work. To do this on Earth, though, we don't have gravity as a feasible way of confining the plasma, because gravity is only strong enough at extremely large scales, larger than the Earth, sort of order of the size of a star, mass of a star anyway. And so we need, in order to try to make fusion work, we need a way of confining a plasma for long enough for it to react using immaterial forces, because you can't just put it in a milk bottle and expect that that's going to, be where your fusion reaction takes place, because either the plasma will immediately cool down or the milk bottle itself will dissolve and become ionized. And fusion research has basically been pursuing two main tracks to do that. One is to use magnetic fields, and that is so-called magnetic confinement fusion, or magnetic fusion energy. And the other is to use what is called inertial confinement. And that is the idea that, well, if we just have a very small assembly of plasma that is incredibly dense and incredibly hot, that the reactions will all take place before it flies apart. So it is, in a certain sense, the inertia of the material of that body that will hold it together long enough for the reactions to take place. And these are magnetic fusion, and inertial fusion is sometimes called laser fusion, because typically lasers are used in order to form these incredibly hot cores of dense material that is going to react. Now, actually, we know that inertial fusion works, not because of lasers, but because the hydrogen bomb, so-called, is a fusion bomb. It is a bomb which is where most of the energy is coming from fusion reactions. But the hydrogen bomb is set off by setting off a fission bomb outside it. And so this comes back to this question of Oppenheimer and so forth, weapons and so forth. Nuclear weapons are ways in which the enormous available energy of nuclear reactions is released very quickly in an explosive way that has enormous power of destruction. The initial atomic weapons, so-called, were fission bombs, but within the next 6 or 7 years, people had learned how to spice them up and make them much more powerful by using fusion. So maybe I should stop there and you push us in a direction that you'd like to go.
Sure. So let's continue with the fusion half of the fission-fusion dichotomy. And I know that you mentioned the magnetic confinement, and one of the things that you're working on is the isolated generation of the superheated plasmas that we've been discussing that reach temperatures hotter than the sun. And this naturally raises about 100 questions, and you've answered at least 19 of them, maybe. But let's start with how you isolate plasma in this way. My understanding is that it's with a toroidal assembly called a tokamak. And maybe we should talk about what a tokamak is and then how it is heated to such literally astronomical temperatures, which I can imagine is a huge engineering feat to be done terrestrially without the huge mass and the consequent gravitational confinement of a star like the sun.
Okay, well, the name tokamak is based on actually a Russian acronym, which just means toroidal magnetic chamber. So just to warm up into this, if you think about the interaction between charged particles and a magnetic field, if there's a magnetic field line, then the magnetic force on a particle acts in such a way that the particle gyrates around the field line. It can also move along the field line. So as it's gyrating around the field line, it can form what is ultimately a helix and move relatively freely along the magnetic field, but it can't move nearly so fast across the magnetic field. So the general idea of magnetic confinement is that we're going to use a strong magnetic field which causes the particles to be basically adhere to or be confined locally to a magnetic field line. And then if we make the magnetic field lines go around in a big circle and come back and bite themselves in the tail, then a particle that moves freely along it isn't lost, it just keeps going around on that field line. And so in order to make that geometric configuration, you need basically field lines that have a toroidal configuration. That is, they have a long path along which they can go and come back and be in the same place. Now, that's an oversimplified view. Actually, it turns out you don't exactly just want circular field lines. It turns out you need to have field lines that themselves are slightly helical, going round in the toroidal direction. Otherwise, it doesn't work. And a tokamak is a description of the simplest configuration that we know that does that, which is to have a toroidal field, which we generate by simply taking a solenoid with currents flowing in a winding, bending it round into a torus. So the fields go all the way around the torus, and then having created the toroidal field, we need a poloidal field to make the field lines also be helical. And we get that by passing a current through the plasma itself, because plasma carries current. And that is, at its fundamental level, a tokamak. There are actually other toroidal confinement devices, that is, donut-shaped devices with a hole down the middle, that cause the field lines to go helically by external windings. The windings are then much more complicated, but they are called stellarators. And in fact, some of the more recent work in stellarators has shown that actually, if we're very, very careful about how we design a stellarator, it can work almost as well and maybe as well as a tokamak. And so that's another magnetic confinement device that we're currently very interested in. So that's how we create, if you like, the magnetic bottle. How do we heat the magnetic bottle? Well, in the case of a tokamak, we've got current flowing through the plasma anyway. So a current flowing through a resistor generates a lot of heat. And actually, that heat is enough to heat the plasma up to, probably maybe 10 million degrees Kelvin or something like that. It's not quite hot enough to get to the temperatures we need to. So we typically, at least I think it's fairly widely agreed, that we need some extra heating. And the way we do that is using radio waves. And that's, in a poor analogy, it's like a microwave oven. I mean, you can heat something up in your microwave oven, basically by microwaves and having them absorbed in the solid material of your food. Well, we can heat plasmas by applying high power radio waves to them and having them absorbed by the plasma. And that works very well. And there are other ways of heating a plasma.
So is it an engineering consideration? How is it that the tokamak is constructed? Like, literally, what are the materials that enable it to withstand temperatures as hot as 10 million degrees, like what you might find in the belly of a star?
The materials out of which the tokamak is constructed don't have to withstand tens or hundreds of millions of degrees. They have to exist separate from the plasma itself. So the plasma itself has to be combined just by the magnetic fields. And so it has to live inside of this toroidal chamber. The way we generate the fields in that is by currents flowing in either copper magnets or normal conducting magnets, but in the longer term and in some existing devices, superconducting coils where the current flows without any dissipation. But this is one of the challenges of this question about how do the material surfaces withstand the presence nearby them of 10 or 100 million degrees Kelvin. The answer is it's difficult because there's a little bit of energy that's leaking out all the time. Some of it's radiated, and some of it comes out in the form of particles. So what we need to do is to have sufficiently well-confined plasma that the heat stays in and very little of it leaks out and then interacts with whatever material surfaces are around the edge of the plasma itself. And that's one of the big challenges of fusion energy.
Well, shifting now to some applications, my understanding, and so you mentioned, I think the figure you cited was roughly, it's 1 million times more effective, or I don't know if the word.
Yeah, there's about 1 million times as much energy in the nuclear force as they're released in fusion in nuclear reactions than there is in chemical reactions.
Right, and then the question then that I have is how, quote unquote, clean is this energy, and then how close are we to actually having replicable, stable sources of nuclear fusion that might displace some of our other less chemical renewable fuels that we're using?
Okay. Well, obviously, one of the things that worries people about the nuclear power that we currently have, which is fission,
right,
is that the fission products are highly radioactive and therefore have to be sequestered for a long time, kept away from people so that we aren't irradiating the workers or the people who are involved in it. Actually, we're very successful at that. Nuclear power is, by essentially all measures, the safest nuclear power that we have. And that's even after you've taken account of, Chernobyl and Fukushima and those other disasters, okay? The truth of the matter is, if you ask how many people have been killed by, let's say, oil or coal or gas, etc., fossil fuels or other fuels, with possible exception of solar power, the answer is it's extremely safe. But of course, there are a number of problems associated with storing long-term fission wastes, and that's one of the attractions of fusion. It doesn't generate highly radioactive materials. It's not without radioactivity. It has because neutrons are involved. There is some activation of the structures around a fusion reactor as we envisage one, and so it's not entirely clean, but I would say very roughly it's 100 times less radioactivity than it comes out of a fission plant. So that's one of the attractions, and it's one of the reasons why people are interested in fusion as a possible energy source. My own view is that fission is indispensable for us meeting the fission. I mean, not fusion. Fission is indispensable for meeting the challenge of global climate change and reducing the CO2 burden of human activity on the atmosphere, and needs to be pursued and is pursued by many countries. But there are debates about how people feel about it. Of course, there's also a sense in which people are nervous about nuclear weapons, and fission technology particularly does enable people who deploy it, in many cases, countries at any rate that deploy it, to develop the technology for producing nuclear weapons. And that issue of proliferation of weapons is a very major one for our globe to think about. In that area, fusion is also far less threatening from the point of view of proliferation than fission is, because it doesn't involve uranium or heavy nuclei that are liable to be used in nuclear bombs. So there are a couple of other things. I mean, fusion is probably better from the point of view of safety. A fusion reactor can never melt down in the way that a fission reactor can if it's not properly cooled. And there's probably more fusion fueled than there is fission fuel on Earth, although both of them have sufficient fuel to supply human needs for thousands and thousands of years. So that's not a near-term challenge. So that's kind of the comparison between fission and fusion in terms of the attractiveness of their potential. But the big difference is we know how to do fission, and we've been doing it, since the 1960s. Fission works, and we know we can engineer it. It is actually quite cost effective, and even though in some commercial markets where the price of electricity goes up and down very rapidly, it's hard for reactors that are designed for base load electricity generation easily to compete in those times when the price goes negative. It is nevertheless economically sensible. Fusion doesn't currently work. We haven't demonstrated a burning plasma with sufficient confinement that it keeps itself hot under its own heating. And that's the near-term goal of some big experiments. There's a big experiment called ITER, I-T-E-R, in the south of France that is aimed to demonstrate plasmas where the self-heating from the reactions, the fusion reactions within it, is sufficient to keep it, pretty much to keep it hot. There's a much smaller experiment, uses very high magnetic fields, that is being developed by a commercial company called Commonwealth Fusion Systems, which was spun off from the MIT work, which I led for a number of years. And they intend to do the same kind of things. It's an experiment, but on a much faster timescale. So I think that there's a chance they will beat ITER to the punch because their costs are very small by comparison. The size of the device is 3 times linear dimensions, which means it's 27 times smaller in terms of volume and mass and so forth. And that's a very exciting development. But even that isn't a demonstration of putting fusion energy on the grid. It's still quite a long way away from doing that. There's a lot of engineering that would have to be developed, and solutions to some of the challenging problems that we've just been talking about that would have to be developed, engineering solutions that would have to be developed before fusion energy can contribute to our electric grid and so forth. By the way, I haven't spent much time talking about inertial fusion, but there have been some important announcements on that front in the last couple of years, where the laser fusion experiments that are conducted at Livermore National Lab in California have achieved a central ignition in which the self-heating of the plasma has been demonstrated to substantially increase by pretty large factors the amount of reactions that take place, and that's been a long time coming. It's taken nearly 12 years since that facility was built before they managed to get it to work as well as it currently has, and they may be able to improve it further. But that's also a very interesting scientific development. That work, by the way, though, is done and funded primarily by the National Nuclear Security Administration, NNSA, which is responsible for the weapons stockpile. And so much of the funding for that inertial confinement work comes because these miniature explosions that they're generating by laser compression are basically models of what happens in hydrogen bombs, but ones in which they haven't used a fission bomb to get it going. And so these are things that we can do, things that our nation does, which are allowed under the test ban treaties and so forth, which I think are very important for limiting the development of nuclear weapons by rogue states and others, but maintaining the U.S. stockpile. So it's what's called stockpile stewardship. But anyway, there are hopes that perhaps inertial confinement fusion might also have feasibility to generate useful energy. My own assessment is that their engineering challenges are considerably greater than the ones for magnetic fusion, and therefore I have somewhat better short-term hope for magnetic fusion than for inertial fusion. But both of them face major engineering challenges before fusion energy could ever become a terrestrial reality.
Well, I'll get back to inertial containment in a moment, though I also think that well, my understanding at least is that there's a fourth type of containment beyond gravitational, inertial, and magnetic that we haven't discussed, which is electrostatic confinement. But I don't know if we want to get back to that. But
I don't think we want to get into that. Let me just say a few pithy remarks about this. We know it can't work.
Perfect.
Basically, the quantitative analysis shows that electric fields are too weak, magnetic fields are strong enough, and gravity is strong enough in a star, and inertial is strong enough on Earth. But electrostatic won't work, and people who say that it will don't know what they're talking about.
Okay. Well, before we get back to the inertial containment, just one quick point that I wanted to clarify regarding your comparison of fission and fusion is why you said, or you believe that fission is vital for combating global warming or CO2 proliferation when fusion is also an option. But maybe you're saying that in the absence of fusion, it's necessary that we continue to work with or investigate fission options.
Well, First of all, I think we need all sources of energy, clean sources of energy that we can develop, because the bringing the CO2 in the atmosphere under control requires eliminating all but a few percent of the fossil fuel basic energy that we use. I don't mean to say that we won't have gasoline, but what it means is it has to be offset by the fact that we made the gasoline in the first place from CO2 or something like that. And I think that people don't realize very often what it's really going to take if we want to get our atmospheric CO2 level under control in terms of eliminating fossil fuel. So therefore, if it's really as difficult as I think it is, and most people think it is, most knowledgeable people think it is, then you need all the full sources you can get. So you need solar, and you need hydro, and you need wind, and you need nuclear. Okay? I don't mean to say nuclear is going to do it all, but you need what you've got. And what we've got in the way of nuclear right now is fission, and we should be deploying it. We don't have we're not in a position at the moment from the point of view of energy policy of saying, no, we don't need fission because we've got fusion. We haven't got fusion yet. We're working on it. It's a long-term research problem. And I don't believe that fusion energy will be deployed on the grid in my lifetime. But long-term, yes, we're going to need other sources of energy, and fusion is one of them. And therefore, what I have been working on through much of my career, I think, is an important research topic, and we should be working on. So that's basically
No, that's perfect. And then getting back to inertial containment briefly. Are you at all involved in thermonuclear weapons research in the form of the hydrogen type bombs? Okay. And the reason that I was wondering...
I have never had clearance, security clearance in the US or in Britain where I started, or Australia for that matter, where I also spent 3 years. So anything I tell you about weapons, I found out from public sources, not from secret sources.
Well, here's the reason why I ask, because it brings in an element of fusion that we haven't discussed yet. And I'm wondering is if it's because this sort of fusion on an engineering level, if it differs significantly from what you're doing with containment, because this fusion is uncontrolled rather than controlled. You're not trying to harness the energy like you are in the tokamak. It's just going out and causing chaos.
Well, certainly one reason why I have preferred to work on magnetic fusion rather than inertial fusion is that magnetic fusion basically can't be turned into a bomb, whereas inertial fusion already is a bomb, okay? And in fact, it works like a bomb. It's basically like setting off lots of little bombs and collecting their energy. I mean, maybe my inertial fusion colleagues will feel a bit peeved by that, but I mean, in broad terms, that's true. So I think that that's the bottom line, is magnetic fusion can't be used for weapons, although it could perhaps be used for proliferation in some other ways. But inertial fusion is about weapons, or about explosions anyway.
Perfect. Yeah. And one of the reasons that this was interesting to me, and we're going to go there right now, is that there are heavy ethical considerations that go into weapons research. And you're I'll just say that, a profoundly religious person. Religion is very important to your life. So let's shift toward that now. And just as I asked at the outset of our conversation what it was that got you interested in plasma and nuclear physics, what was it that captured your interest in the relationship between science and religion? My understanding is that you became religious in college, so maybe that's where we should start.
Yeah. I, First of all, I am a Christian. I believe that Jesus is the Son of God and rose from the dead on the third day. And so I'm basically pretty orthodox in my Christian theology and outlook. And I think that's just who I am. I wasn't always a Christian. I grew up in a family which is not Christian. It was my family didn't go to church. My parents, were, certainly my mother was an atheist, and my father never went to church. And broadly speaking, that was where I stood. I wasn't ignorant of Christianity because I went to a school where it had nominal Christian roots, but I was not drawn to it, and I didn't believe it. And so, even though prayers might sometimes have been said, I didn't pay much attention to it. I was an anti-Christian, but I just didn't believe it. I became a Christian when I was an undergraduate at Cambridge University in the United Kingdom, for reasons that probably I shouldn't go into detail about. But basically, the bottom line was I became convinced that the evidence for the resurrection of Jesus and the evidence for the truth of Christianity as a whole was very powerful and very convincing, and that I was drawn to it in part because I had friends who had attractive lives that were Christians, but also because the commitment to truth and to faith and to loyalty and many other properties I saw as being part of a Christian inheritance. So, that's a very long story. If your listeners are really interested to know more details about the story, they could read my book, Can a Scientist Believe in Miracles?, in which I write down in more detail my journey to faith. But I have been a Christian since I was just before I was 20 years old. I won't tell you how old I am now, but it's a lot more than that. And so if that makes me, a profoundly religious person, yes, I am a Christian believer. I go to church and I pray and I read the Bible and so forth.
Okay, well, I hope that you didn't think I was using the word profoundly in any pejorative sense.
No, I take no offense
Okay,
whatsoever.
great.
And but I do think that there is a certain caricature of religious people, which seems to imply that they're somehow peculiar. And I may be peculiar in lots of ways, and my Christian faith might be one of my peculiarities. I have many others, I'm sure, but I prefer to think of myself as a thoughtful person throughout all of the assessments of the world that I make, my scientific and my social and my religious commitments. And so I don't think I probably quite fit the caricature.
Sure. Well, I am absolutely not interested in portraying you as a caricature on any level, so we don't have to worry about that. But I will certainly, in the introduction, reiterate what I'll say right now, which is that anybody who is interested should absolutely read your book. But if it's okay with you, I would like to ask a few questions about the things that you just elided that are in the book. And so the truth of Christianity, I think, is a great place to begin before we bring science explicitly into the picture. So maybe you could explain just briefly what sorts of considerations took you from someone who did not believe in God to someone who believed in the truth of Christianity. And maybe before you begin, more particularly, what it was that led you to believe in this particular God, rather than, say, the multiple gods of the Hindu religion or the God of Judaism, who, though I suppose is, numerically identical to the God of Catholicism, is believed to have very different properties, in so much as he is, on your view, the father of Jesus Christ who rose on the third day. But that is not how Jewish people would characterize him.
Sure.
Or her, or...
Okay, well, I think you have several questions there. One of them was, why am I a Christian?
Yeah.
I think you're asking in a certain sense an intellectual question. How do I intellectually come to or feel comfortable about the Christian faith? I would say that I approach my faith in an intellectual way, in a certain sense. I don't mean an overly intellectual way. I just think that, the plausibility of the Christian faith is great. And the uniqueness of the Christian faith is that, it lies within the person of Jesus Christ. And I think Jesus is an extremely attractive figure from the point of view of his teachings, of his life, and so forth. He represents a powerful model and an embodiment of truth and justice and love and all sorts of things which I personally think are very valuable. Obviously, in the West, the person of Jesus and of the Christian and the Christian faith in general dominated our society and was in many respects, the birthplace of modern civilization. I don't mean to denigrate, India or China, which have their own civilizations, but the civilization that now powerfully influences the world lies there. But in the end, the most persuasive thing to me was, as I read the Gospels, I felt there was a great truth in them. I think I wasn't unaware of the, let's say, critical theories and discussions concerning, how trustworthy those Gospels might be. But I think that there's a very good argument which says, how did those early disciples, how were they transformed from a beaten group of radicals whose leader had been crucified by the Romans into people who were excited to go out and spread the story, at any rate, that Jesus was not dead, that he had risen from the dead. And I think that if you try to explain how that took place, that it's very hard to do so if you don't take seriously the idea that maybe he really did rise from the dead. At any rate, probably, again, you could read the book for the more detailed arguments, but that's the outline of where the arguments go.
Okay, interesting. And I know one way in which I might push back, and with regard to what you just said about the disciples going from being beaten down to excited, we can also imagine that similar things have happened where people have been beaten down but uplifted by a messianic type figure in other religions. And there, presumably, since these figures aren't captured in the Bible, you wouldn't feel the need to ascribe or some sort of holy component to what is going on here. Well,
yeah, you're implying that Christianity isn't unique in its claims, but I would dispute that. I think the claim of the resurrection of Jesus is basically unique. It's not true that no one ever talked about people dying and rising again. Of course, they did, and in fact, lots of primitive nature religions, have the idea of nature dying in the winter and coming back to life in the spring, and talk about life and death and a cycle of lives. But I think the claim that it actually happened to this one person whom the people were testifying about, I think that is a unique situation, and that discussions of resurrection gods that are discussed in actually in many cases in contemporary religions, contemporary to early Christianity, first century religions, insofar as their actual claims of resurrection are much different from Christianity, except in those cases where they're actually borrowing from Christianity. So I think that the scholarship would say, there are some uniquenesses about Christianity, and that's one of the reasons why I'm comfortable with, if you like, the very particular claims of Christianity. Coming back to what you said about other gods, I mean, it's not the case, I think, that Christians take the view that our God is very different from the Jewish God. I think that actually it's the same. It's just that, Jewish people don't regard Jesus Christ as being divine and part of the Godhead. So of course it's a different religion, but there are lots of similarities. In particular, that it is a monotheistic religion, Trinitarian but monotheistic at the same time. A puzzle, yes, I know. And in that sense, I think that monotheism makes much more intellectual sense of who and what the Godhead might be than do, pantheistic or polytheistic religions. The polytheistic religions of the Greeks and Romans were, in many respects, relatively implausible projections of human society onto the Godhead in a way that I don't think that is true of monotheism.
Well, in response to your first point, I don't think I'm really disputing the uniqueness of the resurrection, but I think what's significant here is that you take historical and other considerations to heart that you find sufficient to merit your belief in the factual character of the resurrection, and that's what's important. That's what's important, and so
I'm not too sure that I would say sufficient, but it's certainly very strong evidence. Okay, I do think that that if you start from a position which says that there can't be a God and it makes no sense, I know that there aren't gods, then I don't think you are going to find the historical evidence sufficient to persuade you. But if you start from a position which is a perfectly respectable philosophical position that asks the question, well, where did it all come from? And is there something that must exist? And is that thing that entity that must exist personal or simply abstract? Then I think that you may well start from a place, and many people do start from a place where they say, well, yeah, maybe there is a God. And I wonder what he's like, or it, or she, for that matter, is like, okay? And if you start from a place like that, then I think the historical evidence is something that makes sense to look at very seriously and take seriously. So I don't feel as though I can persuade someone who already thinks they know that there can't be a God by saying, look at the historical evidence. But I do think that if people were to read the Gospels, with an open mind, they might find they were a lot more persuasive than they think they are. I mean, many people in our modern society think they know what the Bible says, but they don't, because they never read it. So that's that. So maybe not sufficient, but persuasive nevertheless.
Okay, thanks for clarifying what I said. And there are a number of topics at the intersection of science and religion that I'd love to talk with you about, ask you about. But one that comes to mind and that we've already poked at is miracles. And forgive me, I probably have a couple minutes worth of things to say before we get started. But in one sense of the term miracle, an event is miraculous if it's simply a very low probability. So maybe we might want to say, in keeping with our physics discussion, that the birth of a Boltzmann brain is miraculous. But while Boltzmann brains pose their own conceptual problems in a bounded universe with random motion, they're not unexpected. But on the other hand, a miracle could also refer to an event that maybe somehow transcends causation or the laws of physics. And this seems to be in conflict with some core assumptions of science. So what I wonder is how, as a Christian, you look at a purported miracle like Jesus walking on water or turning wine into blood or the resurrection, which we've already mentioned. And if you take these things literally, which I think at least the resurrection, you take literally, how you square it with your understanding of science as something that is concerned with laws, with causation, some sort of rigidity, maybe determinacy.
Yeah. Okay, well, in order to do that, I need to say a few things about what I think science is.
Please.
I think science and physics, one of the sciences, is about understanding the reproducible behavior of the universe. So the way science works is by doing experiments and discovering phenomena and trends in the data and correlations and so forth that are reproducible. And actually, in order to know that they're reproducible, you have to have a special kind of clarity about the way you describe them. And so science also requires a kind of discipline of clarity. In physics, that's predominantly achieved by mathematics, but in other disciplines, there are other ways in which we achieve clarity about the reproducibility of experiments. And I don't mean just that we have to be able to do experiments over and over again at will. So this reproducibility is important also in observational sciences like astronomy. So in astronomy, we don't literally do experiments on stars. What we do is we do repeated measurements on those stars, and that's what astronomy does. Or in its more primitive form, we look up to the sky and we see these reproducible distributions of bright lights, which are stars, and we try to understand them. And that's what science is basically about, this reproducibility. But there is an outlook that's very widespread in our society and in our thinking today, that because of science's great power that's been demonstrated through centuries of successful description of the universe, discovering these reproducibilities, that science is really all the real knowledge there is. And that's an outlook which I call scientism. It's widely called scientism. So it puts science on a pedestal and says science is all the real knowledge there is, and everything else is sort of speculation or wishful thinking or something like that, or just vagueness. So I don't subscribe to scientism. I think there are lots of things we know about the world that are not, in the first place, reproducible, because lots of things in our world are not reproducible. For one example is human history. Human history is full of unreproducible events. We can't go back and reobserve them. We can't go back and redo things. And therefore, there are lots of perfectly respectable disciplines which are not like natural science, that are not based on reproducibility, and to take an example, the historical example, which is based on examining documents and thinking about the plausibility of the times and how people thought and so forth, is an example of something which isn't a science. History is not a science, and so I don't, when I talked about the evidence of the resurrection, it's not scientific evidence, okay? I'm the first to admit that, okay? But if you take the view that science is all the real knowledge there is, then you naturally take the view that, well, religious or spiritual experiences are, not real. They're not about knowledge. They're about emotion or something else that's going on. Okay, so to get back to miracles, if you think that, first of all, physics and so forth talks about the way that the world works when it's behaving reproducible. And we think that the laws of physics are amazingly consistent. And therefore that, basically most things that happen in the world are in fact in accordance with the laws of physics as we understand them. So the question then arises, can anything happen that is not consistent with the laws of physics or the laws of what we discover about the world generally through science? And the answer is that logically, you can't rule out the possibility that there are things that happen that are not in accordance with what we discover from doing reproducible experiments or observations. So logically, miracles are not ruled out by modern science. Now, maybe they're made less plausible by modern science than they seemed to be to people in the 1st century or the 10th century before Christ, for that matter, or whenever, or let's say in medieval Europe, okay? But, and in fact, I think it's a good policy, generally speaking, to say that when people are claiming that there's something that happens in contradiction of the laws of physics or the laws of science, one should be immediately skeptical. And I am. I generally am quite skeptical of things that purport to be different. But I don't think it's logically ruled out. And I think that there are, on occasions, things that happen that we don't have any explanation for, that is, along the lines of the normal operation of the world. It might be thought that it's sort of somehow improper that God would set up a world where he's allowed to break the laws, okay? But I think that actually that's thinking about the relationship between the creator and the creation that is not consistent with the Christian view. The Christian view is actually that the world is continually sustained by God, that God, in a certain sense, holds the universe in his palm, and that if he didn't continue to sustain it, it wouldn't have the regularities that we observe. And so if that is really the right way to think about God, then even though God, as a good ruler, is very consistent about the way he rules his universe, nevertheless, he isn't prevented from behaving in a way that is different and allowing something to be different from the usual way in which the universe proceeds. And so that is the sense in which I am comfortable with the idea that, science is basically extremely reliable, and insofar as we understand the reproducible nature of the world, science is the way we find out about that. But at the same time, there may well be, and indeed I think there are, events that take place that don't have any explanation that's in accordance with the usual way that the world behaves. That's basically the bottom line.
So I will happily agree that logically we cannot rule out miraculous events that conflict with modern science or the laws of physics. And even a militant atheist, which I'm not, I hope would be able to concede that we can accommodate something like the resurrection without having to seriously modify our understanding of physics. But this leads to another and not unrelated question, which is how you read texts that are important to Christian teachings, such as Genesis. So how do you make sense of the beliefs of other Christians also that the world is only 5,000 or 6,000 years old, or that Jesus coexisted with dinosaurs? And to be clear, I'm not trying to trap you or anything like that, or to ask you to defend their views. But there's a serious issue involved in, after having determined that there is a God and the world is a fundamentally religious world, just which of the many religious doctrines is correct and how to interpret the texts that seem to conflict with science.
Yeah, thanks for that question. A very important question. As I said earlier, I take the Bible very seriously. I consider it to be, in a certain sense, authoritative for Christians, and so I read it very assiduously and try to make sense out of these things. The Bible, though, is actually a very complicated book, and actually it's a set of books. And it has lots of different types of literature in it. There's poetry, there's history, there are laws, there are traditions, there are gospels, which are sort of potted biographies, there are letters, and so on and so on. Lots and lots of different type of literature in the Bible. I mean, anyone who thinks seriously would recognize that. One type of literature that there isn't in the Bible, is not in the Bible, is scientific literature. And the reason is because scientific outlook, really the way we understand it today, only dates back to approximately the 17th or the 16th century. And people just simply, in the time when the Bible was written, didn't think in the same way that we think today. They didn't think in terms of the laws of physics or of nature. They might have thought of laws of God, but not laws of nature the way we think of them today. And so I think it's a great mistake to take something like the book of Genesis and try to read it as if it's a scientific description of the way in which the world came to be the way it is. There are Christians who do so, and I think that their approach to hermeneutics is mistaken. I think it's pretty obvious that if you read the first chapter of Genesis, which is where we read about the 7 days of creation, that the main message of that book, of that chapter of Genesis, is not, here is how God made the world. It's not how God made the world, but it's that God made the world. In other words, what was important to the early Hebrews, who were these monotheists surrounded by tribal deities, and probably initially they thought of Yahweh in the same kind of categories as the people of the tribal who had the tribal deities around them. That realization that is embodied in Genesis is that no, actually, if God is truly God, then he's the creator of the whole thing. He's not just another tribal deity that fights for the Hebrews and, the other people have their gods and they fight for them and so forth. In other words, it was a step forward in understanding what it means to talk about God. And that first chapter of Genesis, and we could talk about the succeeding ones, but we probably won't have time. To interpret that as some kind of scientific description of the sequence of events by which the world came to be created it seems to me a foolish way of interpreting the Bible. It's not consistent with the type of literature that is represented by the book of Genesis. And it's not consistent with the situation that the writer of that was writing to the people of the Hebrews in. So, bottom line is, I do read Genesis very much to find out how the people of Israel understood their God and how I should understand God. But I don't feel compelled to turn it into some kind of scientific text and then put it, at loggerheads with the physics that we know today from exploring the reproducible nature of the world.
I'd like to return to something that you mentioned a few minutes ago. You we're talking about scientism, and scientism, I think you've defined it elsewhere as the belief that science is all the real knowledge there is. And beyond the sorts of arguments that you just laid out that are aimed against the structure of what I'll refer to as the scientist worldview, I'm wondering if you see it as also having any particularly pernicious negative social or cultural consequences, the adoption of this sort of outlook.
Okay, well, so I would call it the scientistic worldview.
Okay, that's a good way of putting it.
Someone like me, but that's a small point. So I think, yeah, it is pernicious in lots of ways, because it has important impacts on some of the other disciplines, and also because it has important impacts on science itself. So if scientism is false, as I believe it is, then when people start to say, well, we must follow the science, what that is actually doing is that it's kind of a self-promotional deception. When we make political decisions, and people say we're going to make this on the basis of the science, of course, I believe they should take account of what we know from the natural sciences about the way the world works, and that's very important. But oftentimes, what they're really doing is kind of publicity or actually false advertising. So we're all familiar with the kinds of adverts which say, Wizzo washing powder works better because it's scientifically developed. Okay, that is self-promotion. Okay, and so scientism can lead to a reliance on that kind of argument, whereas in fact sociological decisions, political decisions, need to be made on all sorts of bases in addition to science, and sociological or economic or other related types of discipline are very important, but they're not like natural science. They're not as definitive as natural sciences, and people know that, they sense that. And as a result, when people hear arguments along the lines of, Wizzo washing powder, they're naturally suspicious. And so actually the scientific move, which breeds this kind of false advertising, can actually hurt science itself, because it puts science in a position that it's unable to fulfill, and thereby raises doubts about science in the minds of common people who don't understand what is truly science and what is unknown or uncertain or a different type of analysis from the analyses of science. So I would argue that since you asked me whether scientism is pernicious, I would say that's an example of the ways in which it can be, and often is, pernicious. It basically can alienate people from true scientific knowledge, because it's often being science language is being misused to describe far less scientific knowledge than the natural sciences really addresses. That's one. I mean, the fact that most disciplines are in the process of rebranding themselves as something kind of science, okay, is actually an evidence of scientism at work. So sociology, which is the study of societies, is very important. But actually, what it now calls itself is social science. Well, yeah, it's a very important discipline. There are ways in which sociologists go about gathering the data and trying to interpret it, which pursued in a rigorous and logical way are very important. But they're actually not like how we find out about the world in natural science. They're not based on reproducible, by and large, on reproducible experiments because they're about whole societies. And you can never isolate all of the influences in such a way that you can do what are truly reproducible experiments. So I think that this trend to call, for example, politics political science is an example of scientism at work, where people are trying to catch the coattails of natural science, which has been tremendously successful in producing very profound and reliable knowledge, and apply it to other disciplines. That doesn't mean to say I don't think political scientists, as they call themselves, know something. They do. They know a lot. And politics is very important, and the study of politics is very important, and I want them to go ahead and do it. I just think that it's a mistake if they think they're producing, kinds of the laws of politics.
I'm going to put myself in the shoes or don the hat of the scientism advocate for a moment. And I'm wondering if, because I know that you've done some thinking about past religious scientists and their worldviews, but am I right that what would at first appear to be a positive consequence of the scientific worldview, that maybe like the advances in, say, medical technology in the past 50 years are, in your view, they're not necessarily a product of scientism per se, in the sense that religiously minded scientists like yourself engender serious advances in physics and technology without adhering to this ostensibly rigid and narrow worldview?
Yeah, I think that more or less captures it. I would make the case a bit more strongly than that, and I would say that if you look at the people who were the founders of modern science as we now know it, of the scientific revolution, if you like to put it like that, they were predominantly Christians. And I don't think that's a coincidence. I think it's a consequence, or at least it is a situation in which the progress and the fruitful birth of science was able to take place in a society dominated by Christian worldview, by the worldview of an orderly, created universe. And it didn't take place in some other worldviews, and that I think actually there's a deep connection between Christianity and science in that respect. Of course, even though scientists were predominantly Christians for the first 100 or even maybe 200 years, it's not the case that most scientists are Christians now, although actually, if you were to look at the academy and ask the question, of, let's say, university professors, who are the people who are most likely to believe in God and who are the people who are least likely to believe in God, you might think that if science and Christianity were incompatible, as is often thought, that the answer is that scientists would be the least likely to believe in God. But actually, the statistics and my own personal observations make it clear that that's false. In fact, engineers and scientists are substantially, let's say, more likely to believe in God, people in university positions, than people in the sociology and the humanities. That's simply what the statistics show. So it's actually false to think as many and speak as if you've got a choice. You can either be a scientist or believe in science, or you can believe in God. I mean, that's the kind of crass kind of contrast that's often drawn. So it's not true, and it's actually, if anything, the other way around. That science and Christianity go together very profitably, even though it's, obviously we live in a world that today isn't so dominated by Christianity as it once was.
This is exactly where I wanted to get to, because when talking about Genesis and science, you made clear that you don't consider science and religious beliefs as inherently in conflict the way that someone like Richard Dawkins might. Now, I'm wondering if you see science and religion not only as compatible, but perhaps as simply having different domains of inquiry, just like science and history might. For one, I'm sympathetic, at least to the idea that science, at least as construed as something like the deductive nomological model, though that's contentious and outdated and an idealization of actual scientific practice. I know you're interested in philosophy of science. It can't really answer the question of how we ought to live in the same way that religion might.
Well, there's two sides to this question. One is how do you arrive at ethical and moral judgments? And my own belief is that you can't arrive at those through the methods of science, and you can't even deduce much about them from science, although some things can be deduced. I mean, science does sometimes help you to answer ethical questions because you know what consequences are, for example. But in general, I don't think that any kind of binding moral requirement or ethical principles can be discovered from science. That's one side of the question. But the other side of the question is, well, is there a sense in which one's moral and ethical and philosophical commitments can actually help science? In other words, it's sort of turning the question the other way around. And there, I think that it's pretty obvious that actually they do. I mean, one of the things that science is founded on is the notion of truth and care and correct observation, and that idea of the virtues, largely these are Christian virtues, that go into the reporting and the processes of science are very important. People think that somehow science works by some, abstract logic. Okay, yeah, there's all sorts of logic that goes into it. But actually, the practice of science is very importantly supported by truth-telling, by objective reporting that sets aside my own cares and self-interest in order for the common good of the science as a whole to progress. And these are the kinds of virtues that are historically in the West Christian virtues, but at any rate they're in a certain sense religious virtues. And they're virtues which actually increasingly we find that we can't take for granted. So, one of the crises in science is not just this crisis of physics running out of opportunities, but it is the crisis of what sometimes calls the crisis of reproducibility, that vast numbers of scientific papers are today published that cannot be reproduced. Sometimes that's because they're in very complicated areas, but sometimes it's clearly because people are fudging the data. It's basically falsification. And so that's an example of an area where the absence of a virtue is actually handicapping and dragging down the success of science. So I think there's a two-way street here between what one can think of as being religious virtues and scientific virtues, and I think that that both can actually benefit from each other. So I've said it's in one direction, but I'll say it more clearly in the other. When I'm thinking about people of faith, I think that you need to take seriously the hard work in the process of discovery that has discovered about our world, and not simply think that that is all self-interest. Actually, I don't think it is, and I think a lot of it has arisen from the kinds of virtues that people of faith think are very important too.
Well, Ian, I'd like to finish by asking how you see your work as a scientist in relation to your Christianity, especially since we just talked about how religion informs scientific practice, and we've already seen how it in part contributed to your avoidance of work on inertial fusion. But if you'll permit me an anecdote, I have a very close family friend, like a little sister, the daughter of my childhood babysitter, and she's very Catholic. And she sees her work in environmentally sustainable architecture as work to help preserve and care for nature, which she views as God's creation. So I wonder if you see your work as a physicist as worship in some shape or form.
Quick answer: yes. I mean, there are various aspects of this. First of all, it's been the case since really the beginning of time that when humans have looked at the world and thought of it and seen it as a creation in its entirety, they've been drawn to worship, quite frankly, God. And the Bible is full, for example, the Psalms are full of poetry extolling the wonders of creation. And more recently, I mean, in the scientific revolution itself, there were a number of very important people, Kepler, for example, and Boyle and so forth, who spoke very eloquently about the fact that when they were discovering how the Earth moves, or how in general the universe works, they felt they were thinking God's thoughts after him. They were basically being drawn into a closer relationship and understanding of God through their scientific activities. And I would say, I don't want to be immodest about this. I mean, in general, when I'm solving a differential equation, I don't think I solve it any differently from anyone else, atheist or Christian or whatever. But I do often pause and I'm drawn into wonder at the creation and to give thanks to God. Actually, I think that awe and wonder is common to most scientists, whether they're religious or not, whether they believe in God or not. I think most of them would be able to express some sense of awe about the way the world works. I mean, the amazing consistency of a mathematical description in physics is awe-inspiring, and the way that the cosmos works is awe-inspiring. And in the case of a believer like me, that awe is directed to someone that we think, in some small way, we know. And it becomes a personal expression of worship. So that's part of the story. The other part of the story, I think, for me, is that I do try to act in ways in my science that honor God. And you've alluded to the question about topics of research. That has sometimes, for me, been importantly guided by my moral commitments, which spring largely from my Christian faith. But I think also it bears on the question of how you behave within the scientific community. And while none of us are perfect, and obviously there are always frictions and competitions and various human issues in the practice of science, I do think that the way that I practice science, I try to make as consistent with my moral commitments and my ethical beliefs and what I take to be the virtues, which I possess in some small quantity, but could probably improve, no doubt. So that's another driving force about the way that one acts. I mean, one particular way in which I think specifically the Christian faith has influenced me is that Jesus talks a lot about service and talks about the least being the greatest, etc. And I think that in science as a whole, there's a great tendency for people to blow their own horn, which a little bit of which is kind of okay. But I think that there's a sense in which Christians are called to a kind of servant leadership, in which they recognize their own devotion and, if you like, servitude towards God, and are willing, therefore, to serve others because of God's call upon their lives. And that can work itself out in various different ways. But if you're an academic, for example, professors know that, there have to be department heads. But boy, being a department head is a tough job because, it's a lot of administrative nonsense and you're basically not doing your own research. And yet, I think for a Christian, one is enabled to think in terms of the idea that serving my colleagues is a worthy calling for someone who has allegiance to Jesus Christ. And that's perhaps one of the reasons why, if you look around even a secular university as MIT, you find that actually Christians are amazingly strongly represented amongst the people who are department heads and take on other administrative roles in the university. And I suspect, well, I can't prove it, I suspect it's partly because they see value in helping other people. They are able to take pleasure in other people's success because of that sense of vocation, of Christian vocation to that task. So that's another aspect, I think, of the way in which one's religious commitments can be an important part of being maybe not just a successful scientist, but a scientist who is fruitful in enabling others to be successful.
Well, Ian, this has been terrific on a number of fronts. It was, a great opportunity to talk about what's for me and probably my listeners an underexplored topic in physics. And then I also really tremendously appreciate your willingness to share your views on your faith, especially because this is something people are becoming increasingly cagey and reserved about. So thank you so much for having this conversation with me. It was really a pleasure.
Well, it's been a pleasure for me too, and I thank you for the opportunity to have this discussion.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.